So I thought we'd take some time and talk about scientific and engineering notation. So scientific and engineering notation. So scientific and engineering notation. Let's just start off by multiplying these numbers. Let's take 500 million and multiply that by 300 million. So 500 million, 1, 2, 1, 2, 3, 1, 2, 3, times 300 million. 1, 2, 3, 1, 2, 3. And your calculator may give you something that looks like what I've got up here, 1.5 e to the 17th, right? That's kind of what I've got. Oh, little plus sign here. What exactly does that mean? Well, if we went ahead and we look at the calculator and I put it back in just pure decimal mode, we have a number that looks like this. It's a huge number. And it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 zeros. And I'll say it's got 17 numbers total, or places, before we get to the very first number. So once we get past the first number, we've got 17 places after that, and that is what this is trying to tell us. This is scientific notation, and we'll start off talking about it in terms of powers of 10. Now, you already know about doing powers. We have done 2 to the third, which we know is 2 times 2 times 2. If we did 10 to the third, what would that be? Sure, 10 times 10 times 10. If we did, and that would equal what? 1,000, right? If we did 10 to the second, that would be 10 times 10, and we know that's 100. So the reason we're going to talk about scientific and engineering notation today is so that we can deal with these really large numbers with lots of zeros, or very, very small numbers. So something like this, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that we can accurately write this number down and use it in calculations, you're going to find that you want to use scientific and engineering notation. How would we write this one out in scientific notation? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers total on the right of the decimal place. And so that would be 1 times 10 to the negative 12. So it'll take a little bit to get used to, but after a while it's much easier to write numbers like this, and you don't miscount zeros. It'll make your calculations much, much easier. On your calculator, that might end up looking like 1.0 e negative 12, something like that. All right, so this is scientific notation. Scientific notation, we use powers of 10, and we take our number and we multiply it times a power of 10. So let's make ourselves a little table. So let's do 1 million. So 1 million in scientific notation would be 1 times 10 to the 1, 2, 3, 4, 5, 6 to the 6th. On the left side of the decimal place, we count up to the first number. 100,000 would be 1 times 10 to the 5th. 10,000. 1 times 10 to the fourth, or a 1 with 4 zeros. 1,000. 1 times 10 to the third, a 1 with 3 zeros. We have 100. 1 times 10 to the second, 10. 1 times 10 to the first, we got 1 zero. And finally we get down to 1. That is 1 times 10 to the 0 power. We don't add any zeros. What happens if we go negative now? So we got 1. Let's go to 0.1. Well, this is going to be 1 times 10 to the negative 1. 0.01. 1 times 10 to the negative 2. 1 times 10 to the negative 3. And I think you're beginning to see the relationship. On the left-hand side, we're basically counting the number of zeros, or the number of places to the right of our first number. However, when we get to the decimal place, we're on the right-hand side, we are going to include our first digit. So on the left, the decimal place, it's up to the first digit, so we got 6 places up to the first one. On the right-hand side, we are going to include this, so we've got 4 places, including the 1. So how does that play out with some other numbers? Let's try these. Let's take a look at this. 2.74 times 10 to the fourth. What would that be if we wrote it out in decimal form? Well, what we know is that there has to be 4 places past the first number, since we're at 10 to the fourth. So we'd have 2, we'd have 7 as the first place, 4 as the second, and 2 more. So we would be 27,000. What about 8.84 times 10 to the 8th? Well, what do we know? We have to have 8 places past this first digit. So I'm going to write 8. There's 1, 2, 3, 4, 5, 6, 7, 8. So 8.84 times 10 to the 8th would be 884 million. What would this number look like? 5.4 times 10 to the negative 7. Well, when we see negative exponents up here, that means we're going to be a small number, so we're going to be on the right-hand side of the decimal point. And we know automatically that we have to have 7 spaces, including this one on the right-hand side. So it's going to be 0.1, 2, 3, 4, 5, 6, 7. And there's our number. What about negative 1.2 times 10 to the negative 5th? Well, we know that since it's a negative in the exponent, we are going to have 5 digits, including this first one. And we also know, since this is a negative, this is going to be a negative number. So I'm going to put negative. And here we go. 1, 2, 3, 4. And the 1 will be the 5th one. There we go. There's our number. Now, these are in scientific notation, and they let us take very big numbers or very small numbers and write them in a fairly compact form. These aren't actually huge numbers by any means. As they get larger, using scientific notation is more and more helpful. But what you're going to find is that you probably end up using something else other than scientific notation. It's all built on scientific notation. It's called engineering notation. And we'll look at a few of these numbers, how they would be in engineering notation. Engineering notation only uses the groups that are in powers of 3. So we would use this one. I'll use a different color here. So we would use 10, or 1 times 10 to the third. We would use 1 times 10 to the sixth. We would also use 1 times 10 to the ninth, if I had it up there, and the same here. We would use 1 times 10 to the negative third, and if I had it at 1 times 10 to the negative sixth. So if we take one of our numbers here, if we've got 2.74 times 10 to the fourth, and we said that equals 27,400, we would need to change that to either 1 times 10 to the third or 1 times 10 to the sixth. And I'll show you why one might be better than the other. So it's already in the fourth. So if we're going to change this to the third, we would say there are 3 numbers to the right of this one. So we would end up being 27.4 times 10 to the third. Now if we were going to do this at 10 to the sixth, we would say there are 6 numbers that need to be to the right of the decimal point. I've got 1, 2, 3, 4, 5. So the first one is going to be a 0. And so this same number taken to the sixth, we're going to move the decimal place over 2 places. This is a 4, so we have to move it here. And then one more time. To be able to do that, we're going to have to add a 0 here, right? So we are going to end up with 0.0274 times 10 to the sixth. Now, in our case, it makes a lot more sense to go 10 to the third. Human beings do better with few decimal points than we do with more numbers past the decimal point. Even though it's the same exact number, we would probably find the 27.4 easier to add, multiply, subtract, or divide than we will the 0.0274. Let's grab another one from our example up here. So we did 8.84 times 10 to the 8th. We know that equals 88 million, or 884 million. We would want to change this to either the 6th, this 8th here, to the 6th, or to the 9th. What does that look like when we do that? Well, if we're going to change this to the 9th, we would have to move over the decimal place 1 place, and we would end up with 0.884 times 10 to the 9th. Or if we were going to take it to the 6th, we would have to go, we're at 8 now, so this would be 7, and we'd have to move it here to the 6th, so that would be 884 times 10 to the 6th. So probably this number is the one that I would use, although this would still be accurate. So this is engineering notation, where we put things in groups of 3 rather than just using any number we would like for the exponent. And you'll find this all through the engineering fields where we use engineering notation. So let's try this one. 482,000. You'll notice our little comma here that designates that we have 3 digits. This makes it really, really easy. We could say 482 times 10 to the third. We could use a much larger number. Let's go with 894 million. Again, take a look at our commas down here. We have 6 zeros, 2 groups of 3. So we could say this is 894 times 10 to the sixth. Let's do some small numbers. Let's do 0.001. So let's just count the number of places to the right of the decimal, and we get 1 times 10. There's 3 places, so 1 times 10 to the third. If we do 0.000042, for instance, so I'm going to look at this and I'm going to count, I've got 6 figures altogether, 1, 2, 3, 4, 5, 6, so I can say 42 times 10 to the negative sixth. What if this would have been 0.00000425? Well, it wouldn't have been a whole lot different. Break them up into groups of 3. There's 3 there. There's 3 there. And we would have had 42.5 times 10 to the negative sixth. Or even a bigger, I should say a smaller number. Let's go 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 2, 7. So I've got 3, 6, 9, 12. So I could say this is 12.7 times 10 to the negative 12th. What about if we wanted to go to the negative 15th? We could have, we've got our 3 zeros here, 3, 3, and 3 here. This gives us 12. And I'm just going to add some more to make it 15. There's 12, 13, 14, 15. So we could also say this is, we put these in groups of 3. This could be 12700 times 10 to the negative 15th. Or if we wanted to do this to the negative 9th, there's our 1, 2, 3 there, and so I'm going to go 0.0127 times 10 to the negative 9th. Most of the time, though, you're probably going to call this, you're going to look and see that, hey, I've got a 12 here. When I do 3, 6, 9, and we'll probably choose a 12.7 times to the negative 12th. Again, fewer decimal point places is usually better, as is fewer zeros. So as humans, we kind of like those smaller numbers with not a lot of zeros and not a lot of numbers in the decimal place. All right, so that's how we get numbers in engineering notation or scientific notation. How do we go about adding and subtracting? Let's give this a try. So let's say we have 2 times 10 to the 5th plus 3 times 10 to the 5th. As long as these two exponents are equal, we simply are going to add the 2 and the 3 together, and we would have 5 times 10 to the 5th. Let's do this one. 8 times 10 to the 3rd minus 5 times 10 to the 3rd. And again, as long as the exponent here on the end is the same, we can simply do the subtraction. 8 minus 5 is going to be 3 times 10 to the 3rd. So if they have the same power of 10, we just do the math operation. We can do the addition, we can do the subtraction, and we don't even have to deal with the powers of 10. It just stays the same. What about numbers with different powers of 10? Well, let's try this one. 1.5 times 10 to the 4th plus 3 times 10 to the 3rd. So what we could do is we could keep these grouped 1.5 times 10 to the fourth, and we could turn this one into a power of 4, which would be plus 0.3 times 10 to the fourth, and we could add those. And so we'd end up with 1.5 plus 0.3, which would be 1.8 times 10 to the fourth. Let's do the same thing with a subtraction example. 1.25 times 10 to the fifth minus 2 times 10 to the fourth. We need to get these to the same power of 10. And so let's just leave the 1.25 the same. 1.25 times 10 to the fifth. And we need to move this 2 times 10 to the fourth to a 2 times 10 to the fifth. So we're going to have to move it over one spot. So we're going to have to move the decimal point over, which is going to give us 0.2 times 10 to the fifth. All right, now let's subtract 1.25 minus 0.2 is going to give us 1.05 times 10 to the fifth. So when we're dealing with addition and subtraction, we need to make sure that our powers are the same. And we can change either side. It's not going to matter. But we have to make them the same. I'll give you a quick example. Let's say we have a couple of resistors. And one resistor is 3.74 times 10 to the third ohms. And we would call that 3.74K for those of you electronics students. And we've got another one. We're going to wire them in series, so they're going to add together. That's 9.37 times 10 to the fourth. We are going to have to make these the same. I'm actually going to move this back to the third, so I'm going to have 3.74 times 10 to the third plus 93.7 times 10 to the third. So I've got a 3.7K resistor and a 9.3K resistor, roughly. And we can add those together. And what do we get? We should get a 93.7. I'll just throw the calculator up here. 93.7 plus 3.74. So we get 97.44 times 10 to the third. I've only got 3 significant figures here and here, so we're going to call this 97.4 times 10 to the third. Okay, so addition and subtraction. We need to make sure that we make the powers of 10 equal for all of the numbers. So you're probably wondering now, how do we do multiplication and division? Well, multiplication and division using powers is actually pretty easy. As you're going to see, we are just going to simply add the exponents when we multiply and subtract the exponents when we divide. And so that's kind of the beauty of this whole system. So let's play around with that. So like 10 to the fourth times 10 to the third is going to equal, and we're just going to add them, the 4 and the 3, 10 to the seventh. And if we do 10 to the eighth divided by 10 to the fourth, we simply subtract, and we get 10 to the fourth, right? 8 minus 4. All right, so let's add a more realistic number on here. Let's say 2 times 10 to the fifth times 3 times 10 to the second. So we are going to go ahead and multiply the 2 and the 3 and get a 6. And we are going to add the exponents, that's going to be a 7. So 6 times 10 to the 7th. Let's try a division example. Let's say 10 to the 5th divided by 10 to the 3rd. We should already know we're simply going to subtract, and that should give us 10 to the 2nd. Let's put some numbers behind this. 8 times 10 to the 5th divided by 4 times 10 to the 2nd. Now we're going to go ahead and do the division part for the 8 and the 4 here. 8 divided by 4 is going to be 2. And for the exponents, we're just going to subtract. 5 minus 2 is going to leave us with 3. And so we're going to have 2 times 10 to the 3rd. Let's try a different one. Let's go 12 times 10 to the 3rd divided by 4 times 10 to the 5th. Well, let's go ahead and divide 12 and 4, which is going to leave us with 3. And what is 3? Subtract 5. We're going to get a negative 2. Okay, let's do a quick review. So when we put numbers in scientific notation, we are basically coming up with a way to take very large numbers or very small numbers and write them in a fairly nice compact form. You can see up here in our example we have a million. Changing that to scientific notation, we have 1 times 10 to the 6th. So you can look at our handy dandy table over here. Engineering notation is only going to use the ones that are factors of 3. So we will use 10 to the negative 3rd, or 10 to the negative, or I'm sorry, 10 to the 3rd, or 10 to the 6th, or 10 to the negative 3rd. And we'll just find the number that has the least amount of zeros and the least amount of numbers past the decimal point. Regardless of whether we're doing scientific or engineering notation, when we add numbers or subtract numbers, when using notation, we make sure that all the exponents are the same. So all the exponents need to be the same, and it doesn't matter which one you use. When we multiply and divide, we are simply going to add or subtract the exponent part. I'll take a quick look at that. So when we added these together, we simply did the add operation for the numbers before the powers of 10. When we subtracted, we did the same thing. When we do numbers that don't have the same exponent, we have to change those so that they all have the same exponent, and then we can do the operation. When we multiply and divide, we are simply going to add the exponents or subtract the exponents when we do the division. When we do actual numbers, we are going to multiply this part and add the exponents. When we divide, we will divide this part and subtract the exponents. All right, I hope you found that helpful. If you have any questions, please let me know.